So, let me ask you this. Can a particle pass through a solid wall? In our world, the one we see and touch, the answer is a hard no, right? You throw a ball at a wall, it bounces back. It never ever just pops out on the other side. But what if I told you that when you get down to the tiniest scales imaginable, the rules of the game are completely different? See, in the weird and wonderful quantum realm, a wall isn't really a solid thing at all. It's more like an energy field, a potential barrier. And for a quantum particle, a barrier isn't a definite stop sign. It's more like a suggestion, a challenge to be overcome. Okay, so let's get into how this impossible trick actually works. To really get it, you've got to throw your everyday common sense out the window for a minute and just embrace the quantum weirdness with me.
Think about it like this. It's super simple, right? If you want to drive your car over a big hill, your car needs enough gas, enough energy to make it to the top. If you run out of gas halfway up, well, you're just going to roll back down. You don't just magically teleport to the next valley. That's the classical world for you.
But here's where it gets really mind-bending. A quantum particle, like an electron, isn't just a tiny little ball. It's also a wave. But not a wave in water, it's a wave of probability. This means there's no single exact spot where the particle is. Instead, there's a whole cloud of places it could be. And that probability wave, it doesn't just smash into a barrier and stop. A tiny piece of it actually leaks right through, creating a small but very real chance that you'll suddenly find the particle on the other side.
To make this feel a little less out there, let's use an analogy. Forget particles for a sec and picture a roller coaster instead.
So here's a regular classical roller coaster. It's got a certain amount of energy, but it's just not enough to get over that massive hill. It'll go partway up and then, whoop, right back down. Every single time. It's completely stuck on this side. But a quantum particle is playing a different game. Thanks to this fundamental weirdness of the universe, it can kind of borrow just a little bit of energy out of thin air, just enough to get past the barrier, as long as it gives it back almost instantly. So in that tiny fraction of a second, it's not really climbing over the hill, it's just appearing on the other side. And that is the heart of what we call quantum tunneling. It's this wild phenomenon where a particle just ignores classical physics and zips right through a barrier that it absolutely should not have enough energy to get past. It doesn't break it, it doesn't smash it, it just tunnels straight through.
Now, this impossible leap doesn't just happen willy-nilly. It's all a game of probabilities. So what are the rules? What makes this tunneling trick more likely to actually happen?
Well, it's actually pretty intuitive when you think about it. First, the thinner the barrier, the better the odds. Makes sense, right? A thinner wall is just easier to get through. Second, the lower the barrier's energy, same deal. A smaller hill is way easier to cross than a mountain. And finally, and this is a big one, the less the particle weighs, the smaller its mass, the more likely it is to tunnel. This is exactly why we see it happen all the time with tiny little electrons, but, well, not with baseballs.
Whoa, okay, don't panic. We are not doing any math today.
But the reason I'm showing you this is to make a really important point. This isn't magic. It's not just guesswork. Physicists can use formulas just like this one to calculate the exact probability that a particle will tunnel. All those things we just talked about, the barrier's width, its height, the particle's mass, they're all right there in the equation. It's predictable, quantifiable quantum mechanics. All right, time for a little pop quiz to see if you've been paying attention. Let's go back to our particle that just did the impossible. It's on the other side of the barrier now. What happened to its energy? Is it A, it has less energy because it must have used some up to get through? Is it B, it's exactly the same as before? Or C, does it have more energy? Take a second. What do you think? The answer, and this is pretty wild, is B. It has the exact same amount of energy it started with. No energy is lost at all. This is so crucial. The particle doesn't spend or use up energy to get through the wall. The whole process conserves energy. It's one of the weirdest and most important things to know about tunneling.
So now that we've kind of wrapped our heads around the theory, let's look at how you're using this bizarre quantum effect every single day. And we'll start with the flash memory inside your gadgets.
That's right. Every single time you save a photo to your phone, or a document to a USB stick, or a game to your memory card, you are literally telling billions and billions of electrons to perform this quantum leap. Without tunneling, none of this stuff would even exist. So here's the deal. Inside every one of those microscopic memory cells, there's this little thing called a floating gate. The best way to think of it is as a tiny, inescapable prison for electrons. It's completely surrounded by a layer of insulation, and that insulation, that's our quantum barrier. To store one bit of data, let's say a 0, the device applies a voltage. This gives some electrons just enough of a nudge to do the impossible. They tunnel through that insulation and get trapped inside the floating gate. Then, to erase the data, to turn that bit into a 1, a different voltage is used to yank those electrons back out, forcing them to tunnel out the way they came. Whether electrons are trapped inside or not, that's your data, a 0 or a 1. And quantum tunneling is the only way in or out.
Storing your vacation photos is one thing. That's incredible enough. But tunneling lets us do something even more mind-blowing, to actually see the fundamental building blocks of our entire world. Meet the Scanning Tunneling Microscope, or STM. The way it works is just genius. It has an incredibly sharp metal tip that it brings ridiculously close to a surface. We're talking just a couple of atoms width away. That tiny gap is a barrier, but it's so thin that electrons start tunneling across it, creating a tiny, measurable electrical current. By reading that current as the tip scans across the surface, the microscope can build a perfect atom-by-atom map.
And just look at this. This is what it can do. This is not a simulation. This is not a computer graphic. This is a real image of 48 individual iron atoms that scientists arranged in a perfect circle on a copper surface. Every single one of those bumps is an atom, and we can only see them because of the quantum tunneling of electrons. We are literally looking at atoms. It's just incredible.
So we started with a question that sounded like a riddle, and we ended up with the technology in your pocket and even pictures of individual atoms. It really makes you wonder, doesn't it? If a quantum effect that seems to completely break the rules of common sense is so vital for the technology we have today, what other bizarre, counterintuitive ideas from physics are just waiting out there, ready to be harnessed to build the world of tomorrow?